Good morning, YouTube. This is Vas from Los Angeles. I hope you guys are doing well. I'm doing good. Everything's happy here, so we can start. Okay, SOXL. Why? This 3x leverage semiconductor ETF. We're gonna review quickly this guy, and we're gonna jump on the nuclear power and AI. So first, as you know, we got the surprise early this week, and I decided to kind of liquidate my investment. It's like roughly, I got 30%, 30% profit, not bad. I'm waiting to see what's gonna happen next week. It's gonna fall, it's gonna bounce back here, or we're gonna see bigger correction like this guy. Imagine if it goes down to this curve on the bottom limits here, then we're gonna have opportunity to get this to buy this ticker at the price of $10 something. Right now it's $35, not bad. Let's see how it goes. Well, sometimes things goes wrong way, like this one. Anyway, the main topic of today is AI, general intelligence, AI, and basically relation to that to the NVIDIA and power. So we're gonna start with a paper that is published on November 2020, November 6, 2020 from OpenAI. In this paper, they talk about something important called reducible loss and amount of computation. This is 2020. Don't forget, this is ChatGPT 3 in that era. I'm pretty sure they add more of computation, more of the models, things like that. So in this paper, they give us six different charts: language, math, image, etc. And one of them is about language model, ChatGPT 3, basically. On the x-axis is reducible loss, which means how accurate it can work. If the error, things like that, how much error they can reduce. And on the right axis, on the left axis is reduced loss. On the right axis, it's amount of parameters, 10 to the 11th. This is logarithmic scale. On the left axis, reduces loss is a linear scale. This goes down from 6, 5, 4, 3, 3, 2, 1.5. So if this goes to the zero, basically you're gonna have perfect model. Whatever you ask, the answer is perfect. The other side is the amount of parameter they need to add. So as you increase your model, you can improve the accuracy. The x-axis here is something called computation, peta floating point per second during the day. Wow, a lot of things to cover. So we're gonna go through this and see how much hardware it requires, how much it costs, and how much power that hardware consumes. Okay? Okay. So let's start from floating point computation and what that is. So floating point per day computation, its unit of measurement for computation. One petafloating point per second day is the amount of compute that results from running one petafloating point operation per second for 1 day. So imagine you write your program, you hit the enter, it's gonna run text 24 hours, and it's gonna do peta. Peta means 10 to the 12. Yes, 10 to the 12 floating points. It means you have a number 10, number 1, and 12 zeros on the front. This is 1 peta. Floating point is basically you have a number like 1.2. This is in floating point. You have a floating point. Okay, so it's ridiculous amount of. So how much? What hardware do we need? I don't have access to all the information, but the hardware's from NVIDIA. But one thing we can do is we can go with the Tesla 800 graphic card that has a Tesla that has a NVIDIA AI chip on it. For it's mainly used on the training. As you see, it can do roughly 10 tera floating point. What does it mean? It means, let's do some quick math here. It does 10 tera. So in order to do this chart here, let's say 10 to the 0, which is 1 petafloating point per day, you're gonna need how many? If you want to do 1,000, you're gonna need 10 of them. Roughly speaking, yeah, it is 9.8, 100 of them. Yes. So this times that is 1,000. This is equal to the 1 floating point, basically peta floating point per day. 1. How many hardware do we need? We need 100. Yes, we need 100. 100 graphic cards. How much it costs each graphic card? This guy, how much is it? Last time I checked, it's like a $1,000. So, wow, it varies a lot. Look, mm, okay, it says 20 grand, roughly $20,000. Okay, let's say $20,000. This guy, 20 grand, 20K. Okay, it's gonna be this times. Okay, quickly, I guess we're gonna reach to the uh, million. So I'm gonna divide this by 1,000 to say this gonna cost $1,000,000, $2 million. Okay, dollars. And how much it consume? Um, it's like a 300 watt maximum. So we're gonna have, this is like a 300 watt. We're gonna use 100 of those. Okay. This is like a 30 kilowatt. I'm gonna divide it by 1,000. It's kilowatt. Soon, I guess we're gonna reach to the million. So I'm gonna divide it by million. This is like a megawatt. Yeah, it's 0.03 megawatt. So this is much better. Now we want to see how much error we get. Loss, basically. Loss of the model. So in the loss of the model, for the loss, it says we can use this equation to understand the loss. L equal to 2.57 is equal to 2.57 times this number, okay, it says C, which is this guy, to the power of minus 0.048. Okay, to the power of minus 0.048. Is it 48? Yeah. So 0.10, it should roughly give us 2 point something, 2.7. Yeah, 2.57. Okay. So this is equation is correct. Now we want to increase it. It says 10 to the 4 means we're going to add 4 more zeros. Yeah, if we add 4 more zeros, these 2 times 4 more zeros. Uh-huh. Right. This is the amount of graphic card you need. So let's do this with that too. 4. How much it's going to cost? It's going to cost quite a bit of money. Look, you're already in $1 billion. How about we do $1 billion? Equal to this, divide by 1000. Huh? It's like $10 billion worth of hardware. That's a lot of hardware. Wow. How much power? Okay. You go down. 300 megawatt. You're gonna burn 300 megawatt hour for 24 hours to do this calculation. Okay. And if you want to increase more, by the way, this is you do 1.5, 1.65. How about if you want to go lower? Just add more 4 more zeros. You go loss of 1. Basically, you add 4-fold to your computation, but the loss is reduced only by zero point 0.6. Okay? How much graphic card do you need? This much? It's a ridiculous amount of graphic card. It requires $2 trillion worth of hardware. You're gonna burn, let's say, megawatt, gigawatt. How about we do in gigawatt scale? You're gonna burn 3,000 gigawatt, almost 1 terawatt. How much United States, how much electrical power United States produce? United States power is 4,230 terawatt hour. Okay, let's go back. 4,230. Where is it? Here. 4,230 terawatt hour. Terawatt hour. Okay, this means we are almost 0.1% of US consumption. If we translate it to the terawatt, this is 3 terawatt. Okay, let's double check. Okay, so still the loss hasn't reached the 0. But what if we want to really force this to go to zero. Let's see, maybe we can do this. It's easier. Oh, oh, okay. Let's see whether we can do this. This is scientific method. Scientific. Okay. Okay. 10 to the 12. Wow, that's a lot. Okay. So finally, we reduced the losses by zero point 0.4, zero point 0.3 roughly. And how much this gonna cost us to do? You're gonna consume, wow, that's a lot of power. This is a lot of power. 30,000 terawatt, more than what United States can produce today. Is it right? Wow. Holy cow. Okay, this divided by that. It's 7 times more. And still you're not in zero. Wow. I don't know what these guys are thinking, but based on just simple calculation, you're gonna need a lot of power. A lot of power. So this brings the question, who gonna provide this amount of power to make a zero loss AI, which it becomes artificial general intelligence? How we can do that? I guess the only answer is uh, nuclear power. So it's good to know who are the main players here. I create a chart that shows almost all the top ones, and some of those, as you see, well, from just early this year up to now, they become very profitable. SMR is like 481% up. Let's add the NVIDIA for just comparison. I'm gonna make the NVIDIA yellow. So what's up? Okay. So this is roughly twice of that, or 3 times, 2.5 times of the NVIDIA. It's a lot. NVIDIA roughly 200%, 3 times. This is like 481%. Wow. Who's the next? CEG. This is up 134%. These guys are main players in nuclear power. Nuclear power become real deal things. Look at this one. LEU, of course. Whoever works on this today, it become rich in future. Why? Just simply because of this guy. You need lots of power and lots of money. Hmm? You need ton of money and ton of power to make an AI, to make an accurate AI. Yeah, the general intelligence should be accurate. You type something, you want to get accurate answer. Basically, this loss should go zero, and that's what they are hoping for. They're gonna print ton of money, and all of them will go to the NVIDIA and this nuclear powered research centers and manufacturers to make the AI happen. Okay, that's it. We're gonna talk about more about these things. I'm gonna work on this to see how accurate the numbers are. The graphic card for 20K sounds ridiculous. I guess it should be cheaper. but this is just graphic card. The NVIDIA is making a very fine-tuned chips to help AI. So probably the power consumption may be lower. It has a better floating point, higher floating point computation, but I don't think it's gonna be a magic. The number may be gonna cut in half, but it's not gonna be reduced by a factor of 10 or 100. Don't forget, this is for numbers for the one day. Yeah, if you want to do those computation in one day, you can say, okay, instead of doing 30,000 terawatt, you're gonna in one day, you're gonna distribute it in 10 days. This is gonna be 3 terawatt, or you can do it in 1 year, in 100 days. Then it becomes 300 terawatt, which means you're gonna run your program, you're gonna hit the enter. The machine gonna run for 100 days and gonna return the result after that, something like that, basically. Okay, um, that's that. Let's go back to the my favorite ticker, XOXL. It's doing poorly these days. Come on, man. We should go high. Hopefully next week we see something. But again, only paranoid survive. If this goes down, better opportunity. This is semiconductor. Everyone needs semiconductor. AI is semiconductor hungry. It's like a burger. You're gonna need them. They're gonna need them. Everyone needs these things. Okay, keep in touch. Have fun. Have a good day. And bye bye.